Hello everyone, welcome to the channel. So we'll be taking a look at the circuit analysis in today's video. So let's get started. The first one is a network. So what's a network? A network is basically an electric circuit which has a source of EMF and circuit elements present in it, which can be resistor, inductor, capacitor, diode, transistor, etc. Now network can be of various types. The first one is active and passive network. So, if a network has one or more sources of EMF present in it, it is an active network. Otherwise, it is a passive network, as you can see here in the diagrams below. Now, the second one is linear and non-linear network. So, if the current in all the branches of the network is directly proportional to the driving voltage, it is a linear network. Otherwise, it is a non-linear network. Now we will be taking a look at the four-terminal network, three-terminal network, and two-terminal networks. Now, if the network has two input terminals and two output terminals, then it is a four-terminal network. In the case of two-terminal network, we have one input terminal and one output terminal, as you can see here in the diagram. In the case of three-terminal network, we have one input terminal, one output terminal, and one common terminal. Now let's take a look at the electric sources. Now electric sources are of two types. The first one is a voltage source, the second one is a current source. First we will be taking a look at the ideal voltage source, then we will study real voltage source. So a voltage source without an internal resistance is an ideal voltage source. What happens in an ideal voltage source is that it provides a constant voltage regardless of the current elements present in the circuit. As you can see here, the ideal voltage source is providing a constant 10 volt regardless of the load resistance present in the circuit. Now, an ideal voltage source is a theoretical concept because if load resistance is tending to 0 ohm, load current should be tending to infinity, which is not possible. What happens in reality is that every electric source has an internal resistance. In the case of real voltage source, internal resistance is connected in series to the ideal voltage source, as shown in the diagram below. The internal resistance is in the series with the ideal voltage source. Now we'll be taking a look at the current source. An ideal current source provides a constant current regardless of the current element present in the circuit. As shown here in the diagram, ideal current source is providing IS steady current regardless of the change in the load resistance. In the case of real current source, internal resistance is connected to it in parallel to the ideal current source. As shown here in the diagram, the ideal current source has an internal resistance Rs connected to it in parallel. Now, if the Rs is equals to infinite, we get an ideal current source. Now, ideal current is passing through the load resistance RL. We can find IL through this formula. Now let's take a look at impedance. The first one is linear and non-linear impedance. If the current flowing through an impedance is directly proportional to the potential difference across its end, it is called linear impedance. Otherwise, it is called non-linear impedance. Inductor, capacitor and resistor show linear impedance, whereas diode and transistor show non-linear impedance. Now let's take a look at the bilinear and non-bilinear impedances. If the impedance of the element remains unchanged by reversing the direction of the current, it is called bilinear impedance. Otherwise, it is called non-bilinear impedance. Inductor, capacitor and resistor show bilinear impedance, whereas diode and transistor show non-bilinear impedance. As shown here in the diagram, if the current is flowing from left to right, resistors show R impedance, or if the current is flowing from right to left, resistors show R impedance. In the case of diode, if the current is flowing from left to right, diode show zero resistance, whereas in the case of current flowing from right to left, diode shows infinite resistance. Now let's take a look at the mesh and loop. Mesh is the closed path in the electric circuit which doesn't contain any other closed path in it, whereas loop is simply a closed path in the electric circuit. Now, in the loop A, B, D, A and B, C, D, B, both are loop and mesh, whereas in the case of A, B, C, D, A, it is a loop, not a mesh, because in it there are two more closed paths present in it. Now let's take a look at node and branch. A node is basically a junction where two or more elements connect, and branches are the connections between nodes. So node A connects electric source and R1, whereas node B connects R2, R1 and R3. Similarly in the cases of C and D. Now branch AB connects node A and node B, whereas node branch BC connects node B and node C. Similarly in the cases of CD and DA. Now let's take a look at the Kirchhoff's law. The first one is the Kirchhoff's first law or the current law, KCL. Now according to this law, the total current entering a circuit junction is exactly equal to the total current leaving the same junction. Or we can say the algebraic sum of all the current entering or leaving a junction must be equals to 0. As shown here, the summation of I in is equals to summation of I out, or I total at a particular node must be equals to 0. As for the sign convention, the current entering a circuit junction is taken as positive, whereas current leaving the junction is taken as negative. From this diagram, we get I1 and I2 entering the junction taken as positive, whereas I3, I4 and I5 leaving the junction taken as negative. So from the law we get I1 plus I2 is equals to I3 plus I4 plus I5, which also shows the conservation of charge as there is no charge left at a particular node. The second one is Kirchhoff's second law or the voltage law, KVL. Now according to this law, the algebraic sum of all voltages around any closed loop in a circuit is equals to 0. That is, summation of V total for any particular closed loop is equals to 0. Now pay attention that we are using loop here, not a mesh, so we can take any closed path in an electric circuit. As for the sign convention, when we travel from negative to positive direction, the EMF is taken as positive. If we travel from positive to negative direction, the EMF is taken as negative. For example, if we are traveling in clockwise direction, so for EMF E1, we are traveling from negative to positive, so that is from lower potential to higher potential, it will be negative. As for the E2, we are traveling from higher potential to lower potential, so it will be positive. As for the circuit element, if we are traveling in the same direction as the assumed current, EMF will be positive and vice versa. Now for the loop A, B, C, D, E, F, A, we start from A and go in clockwise direction along the loop. Now let us assume that at node A we have potential VA and at node B we have potential VB. So VA minus VB will be I1 R1 because we are traveling the same direction as the assumed current. As for the branch BC, VB minus VC is equals to I2 R2 because we are traveling in the same direction as the current I2. As for the branch CD, Vc minus Vd will be equals to negative of E1 because we are traveling from lower potential negative to higher potential positive. For the branch DE, Vd minus Ve is equals to I3 R3 because we are traveling in the same direction as the assumed current. As for the branch EF, Ve minus Vf is equals to negative of I4 R4 because we are traveling in the opposite direction of the current I4. As for the branch FA, Vf minus Va is equals to E2 because we are traveling from higher potential to the lower potential, plus to minus. Now adding all this, we have I1 R1 plus I2 R2 minus E1 plus I3 R3 minus I4 R4 plus E2 is equals to 0. From this we get this I1 R1 plus I2 R2 is equals to I3 R3 minus I4 R4 which is equals to E1 minus E2, which shows that this law is also based on the conservation of energy. Thank you and have a nice day.